Okay, well done. Last section then on medical physics. This is in 3 parts. First part about sound and ultrasound. We're going to have a quick reminder about sound wave, stuff that you did in year 9. We're going to look at what ultrasound actually is, and we're going to look at how we can use it, particularly how we can use it in medical applications. So, remember the wave diagrams we've got. There's 2 different things that you can change about waves. We can change the pitch of the wave, can be low or high, and we can change whether the wave is quiet or loud. Here's some pictures. You might want to pause the video, see if you can match them up. So here's a low pitch and a quiet noise, and here's a high pitch and quiet. You'll notice the height of the wave isn't very high, that's telling you it's quiet. This one there's not very many waves, this one there's lots of waves, that makes it high pitch. So this one is loud because it's got a big height there, a big amplitude, and this one is also loud but it's high pitch because there's lots of waves. So we can start using sound, particularly in this part, in echolocation, which tells you what it is. Echo, the reflection of a sound. Location, finding where something is. So we're finding out where things are by the reflection of sound, and this uses ultrasound. Human ears can hear, at least when you're young, between 20 Hz and 20 kHz, 20,000 Hz. If the sound's above 20,000 Hz, it's called ultrasound. Things like whales and dolphins use ultrasound, and also bats for this echolocation. They're making the sound, they're listening to it coming back, they're judging by the time it takes how far away an object is. So this is a high frequency sound which is produced by an animal. The sound hits the object and is reflected, which is what we call in everyday life an echo, but we should more scientifically call it a reflection. The animal can locate the object using highly evolved ears, so it's got to be able to make the sound and detect it itself, and it senses the time for the echo, the sound, to return. Okay, we've adapted this for use ourselves as human beings. A little example of this is a trawler. So this is sonar, stands for sound navigation and ranging, and it uses the same sort of principle. This is a little bit simpler, so we can look at it just to get us into the idea. So the sound comes down, it hits the bottom of the sea. You see how long it takes for the echo to return. That tells you how deep the water is. There's a little trap. It's 1500 meters per second. That's the speed of sound in water. It takes 4 seconds between when you make the sound and when the echo comes back. How deep's the water? It's a little bit tempting to do 4 times 1500, because distance equals speed times time. 1500 times 4, 6,000 meters. So if you're not careful, you'll stop there and say the sea's 6,000 meters deep. But if you think about it, the sound's had to go down and back again, so it's only half that deep, 3,000 meters. Okay, something that gets us into thinking about ultrasound in medicine is that actually sometimes what you want is for some of the sound to carry on and some of the sound to reflect back. This is called a partial reflection. Some of the sound reflects, some of it doesn't. So if you've got some fish in the way, then you make the sound. Okay, we're a bit shallower here, so the echo is heard after 0.2 and 0.6 seconds. How's that happened? Well, what's happened is you've made the sound. Some's hit the fish and reflected back. Some's hit the bottom of the sea and reflected back. So the echoes come from 2 different places. How deep are the fish? Well, it took 0.2 seconds for the sound to come back. So distance equals speed times time. 1500 times 0.2 is 300. So the depth of the fish is 150 meters. Same sort of calculation. The depth of the ocean is 450 meters. You might notice that the amplitude went down because the amount of sound went down when it was reflected, but the frequency stayed the same. Okay. Apart from in medicine, there's some more uses in industry. So you can clean delicate items. You don't want to get a kind of sandpaper or something on a watch to clean it, because it's going to destroy the mechanism. So they shake it very, very quickly in what they call an ultrasound bath, and that just shakes little bits of dirt off it. Also on bridges, suspension bridges are held up with these wires. Sometimes these wires can break inside. You get little breaks inside them. They're designed to cope with some of those, but if you get too many, the whole thing's in danger of falling down. So you send a pulse of sound along it, it reflects back, and you can see if it's reflected back inside the cable. You can even work out how far along the cable the break is. Okay, here's some medical use, little animation to show you. So if we look at the first bit, this is making an ultrasound outside the skin. Here's the liver inside the body. You'll notice that when the pulse of sound is made by the ultrasound probe, some reflects off this first change in density, so it carries on through the skin until it reaches a different density. Some of it is reflected, some of it carries on, some of the stuff that's carried on reflects off the second surface. So you get these two dots. Here's the reflection from the top, here's the reflection from the bottom. If you then scan across the liver, then you get a whole series of dots. You can start to work out what shape the liver is. So most of you will be familiar with ultrasound imaging from looking at fetuses, unborn babies. Here's a little image of a foot. We've now developed a technology that can go 3D ultrasound, so computers can take this kind of information and they can turn it from a 2D image by looking at different depths into a 3D image. So you start to see these kind of pictures, which looks a lot more like a foot than an old-fashioned ultrasound scan. Okay, you can see lovely pictures of your unborn child in the womb, all in 3D and looking lovely, and even these days in 4D, where you can actually have a video of that. The surface is computer rendered. You're not really quite getting this image by ultrasound, but the computer is kind of fleshing it out and literally putting the flesh onto the bones and the other organs. Just a few little things about safety in ultrasound. When the ultrasound doesn't reflect back, some of it's absorbed, that causes heating, but we've been using ultrasound scans for about 50 years, so people are pretty confident those are safe. 4D ultrasound, which is 3D plus time to make the fourth dimension, needs more energy, which generates more heating. At the moment people think it's safe, but you might get a question on kind of ethical issues of doing this. So what are the ethical issues? Well, if you think there's actually an illness and you can diagnose that illness like this, it's a very small risk, so it's probably worth taking. If it's just that you like to have a nice video of your baby and you're thinking that that will be nice to kind of look at in years to come and show him when he's older or whatever, all right, then maybe it's not worth that risk until we're 100% sure it's safe.